The following simulation shows a damped oscillation as well as the phase diagram for the phase oscillation, which is basically just the x and the velocity plot of the motion. And so in this video, we'll be discussing about oscillation, and we will later go into more details into the equations as well as every single thing that results into these types of motion. So before we get started, you might as well check the description below for the timestamps throughout this entire video for you to skip through just in case if you already know some certain topics. So let's just straight away with the introduction. So first of all, why do we discuss about the oscillation first of all? And this is because if you have a conservative force, or technically a force that doesn't depend on time but instead only depending on the position, you could express this in terms of a Taylor series around 0. So we could state that f0 plus the df over dx multiplied by x plus the d squared f over dx squared 1 over 2 factorial x squared and so on. And so for most forces, we could actually just assume that the higher terms would be 0 if you do a very small propagation. So this would go to 0, and also you could define your x equals to 0 when the force is actually 0. So you could just denote this to be 0 as well. Thus you have this df over dx equals to x, in which we'll denote this as negative kx. And so we have the following force to be F equals to negative kx, which is basically something which you call as Hooke's law. And so this will be the thing that we'll be using throughout this entire video. And also, you could later introduce some damping, in which the damping will be introduced to be negative BV. And alongside that, you could also add a external force which depends on time, which will denote that as F with the function of time. So this will later be a simple harmonic motion, simple harmonic oscillation, damped harmonic oscillation, and lastly, it will be a driven. Well, so it's a damped harmonic oscillation and driven harmonic oscillation. Or we could also call this as forced. It's the same thing. So let's just jump straight away to simple harmonic oscillation. So let's say if you have the following problem. Let's say if you have a spring and you have a mass here, and we'll denote this to be x equals to 0 when it is at rest, when it doesn't experience any force. And let's say it starts with a initial condition, so this is positive x, such that if this is x equals to 0, this is the force. No, sorry, this is the location of the mass, located at x. So later this will have a force going backwards and there's no other force. So therefore, you could denote this to be negative kx equaling to mx double dot, which is the equation of motion. So you could solve this differential equation and you could get this to be, so if you simplify this, it's negative k, let's do it like this. X double dot plus k over m x equaling 0. So to make this much more simpler, you could just denote the square root, no sorry, we could denote the k over m to be omega 0 squared. And this will actually give us a very elegant solution. So trying to solve the problem, you know that for this type of differential equation, it should be a sine or cosine based on a guess. So this would be, so we'll denote this as cosine because this is what we normally write this as. So it's cosine omega 0 t minus a phase difference. And multiply this with a amplitude. And this will be the equation of motion. And so this is the exact equation of motion for a harmonic motion. And so this is the general formula for you to solve any type of simple harmonic oscillation. It's x equals to a cosine omega 0 t minus phi. And you might need to add some additional constant the because of the initial condition where the force is not zero. And so this is actually the general form of the equation of motion. And so you might be thinking about what about the energy of such motion? So we could actually figure that out. So one of the easiest things for you to think about is the velocity first. The velocity could be obtained straight away to be negative a omega 0 sine omega 0 t minus phi. This is coming from the derivative of the position. And so you could get what is the kinetic energy, which is half mv squared. Thus, this would be ma squared omega 0 squared over 2 of sine squared omega 0 t minus phi. And so you could actually take this omega 0 squared and convert that into the k over m. So you would get another form which is ka squared over 2 sine squared omega 0 t minus phi. Now you might be thinking, what about the potential energy? So we could also do that. So if you remember that starting from a initial position, let's say this is at 0, which will be the reference point, until the point x of the force, which is negative kx, dx must be equal to the negative of the potential energy difference. So it's the u at x and u at 0, which will denote this to be at 0. So let's just try to figure this problem out now. So the potential energy with respect to position will later be kx squared over 2. So you could just do the integral straight away, and x would straight away become x squared over 2. And so this is the potential energy in general for any type of spring or anything which has this linear force. So we could plug in what the x is. So this would be ka squared over 2 of cosine squared omega 0 t minus phi. So now asking about the total energy, you could just sum them both up. The kinetic energy plus the potential energy, you would get that this would just be ka squared over 2. And this is something elegant. You see that the energy mostly depends on the A for the same type of physical system. And so A is the one that determines the total energy. So it's based on the amplitude. And alongside that, we see that the energy doesn't depend on time. So this is actually so we see that the energy is conserved. Similarly to what we actually observed previously, in which we expect that if you have a conservative field, and one such example is F equals to negative kx, the energy should also be conserved, which we see here. So let's talk about some of the notation, but first we could just see that actually this is a oscillation, right? And so we know that omega 0 t minus phi, so let's say omega 0 t minus phi would be 0, and it will later repeat itself after a certain time. So omega 0 t plus some additional time minus phi would be 2 pi instead of 0. So it's 2 pi. There we go. So this would basically denote that it has done a full rotation. And so you could solve what tau 0 is. So just subtracting both of the equations together, you would get omega 0 tau 0 would be 2 pi. And so what you would get here is tau 0 is 2 pi over omega 0. And this is what we call as the period of the oscillation. So this is the time that it takes for it to go back to its original position. And if you have already taken General Physics 1, you'd also notice what omega 0 actually is. Omega 0 in here is something which we call as the angular frequency, which is the radians per second. And you could also try to flip the tau 0 to become 1 over tau 0, which is what we call as the frequency. It will be omega 0 over 2 pi, which we call as the frequency. So something to note here is that these three different quantities doesn't depend on the energy or the amplitude. And this is what we call as isochorous, in which they don't depend on the amplitude of the system. So let's try to solve some other problems in which it might have a linear function. Sorry. So let's try to solve some other physical problems that might have this linear force. So one such example is a pendulum. So if we have a pendulum here, something like so, with mass, and it has angle theta. You might be thinking to solve this in the Cartesian coordinate, but it's actually much more simpler if you solve it in the polar coordinate, or even using the angular velocity, angular acceleration, and all of those. And so I haven't really discussed much about how you use it, so we could just use the idea from General Physics 1 first, just to remember that the torque would be I times alpha, the moment of inertia, multiply that by the angular acceleration. So let's try to solve this. So torque is defined to be R cross F. And so in here, the F here is this one. And so it would have this angle like so, right? And so what's the torque? Let's say the length of this pendulum is L, and therefore you could get what the torque is. It's the length, multiply that by the force sine theta, which will later denote to this small component in this direction. And this torque must be equal to the moment of inertia. And so the moment of inertia for a single point would be just mr squared. So it's ml squared, multiply this by the angular acceleration, which is theta double dot. And this is basically the equation of motion. So we could simplify this much more further. Oh, sorry. So the force here is going to be mg. So let's simplify this. We could get, oh, sorry. This should be negative lmg because it's going in the opposite direction of the theta. That's something to note. So we could simplify everything to get theta double dot plus g over L sine theta equaling 0. And this doesn't seem to be a harmonic motion. But if you look at the details, you would notice that sine theta in itself has a Taylor series which corresponds to a theta. So for very small angles, you could just assume that this would be theta double dot plus g over L theta is equal to 0. And now you could denote what g over L is. We could call g over L to be the square of the angular frequency. And so you would be able to obtain what is the equation of motion, which will later denote the movement of the theta. And you would see that it's actually a simple harmonic oscillation for very small theta, obviously. So that was all within one dimension. And so we could actually try to think of something much more elegant. We could try to think of this in two dimensions instead. 2D harmonic oscillation. So let's consider the idea in which if you have, let's say, a framework here, and you are putting your springs here, something like this, or actually, you know what? Let's don't do it like that. Let's do it like this. to make it much more simpler for us to analyze. Something like so, and the spring here can move freely as long as they are still perpendicular to the mass. And so basically there will be two Ks, K1 and K2. But in here, we'll be assuming K1 equals to K2 first, because this would be the simplest condition. And so if you observe the movement, if you actually displace it much more further in this direction, it will oscillate something like this. And if you displace it in this direction, it will oscillate something like this. And so the question is, what's the exact equation of motion for this particular object? So it's solvable. We could just right away do mx double dot equaling negative kx and my double dot equaling negative ky. And because the k1 and k2 is the same, right? So we could denote that to be k. We could actually simplify this straight away into two different equation of motions. The first one, x, would be a cosine omega 0 t minus alpha, and the y would be a cosine omega 0 t minus beta. So instead of writing the y like so, let's actually just write that as a cosine omega 0 t minus alpha plus alpha minus beta. And let's try to solve this. Oh, sorry, this should be b, because they could have two different amplitudes. So we have something like this, and we can probably expand this. So remember that cosine a plus b could be expressed into cosine a cosine b minus sine a sine b. So if you denote this to be the delta, we could get this to be b times cosine omega 0 t minus alpha cosine delta minus sine omega 0 t minus alpha sine delta. And so you could denote the cosine omega 0 t minus alpha, the cosine of omega 0 t minus alpha, to be x over a. And so you could get what is the cosine as well as the sine based on the trigonometric function for sine, which is going to be the square root of 1 minus cosine squared omega 0 t minus alpha, right? So we could simplify this to be b x over a cosine delta minus the square root of 1 minus x squared sine delta. Oh, sorry, this is x squared over a squared. And this would be the y. And so we can multiply both sides by a. So we would get ay equaling bx cosine delta minus the square root of a squared minus x squared sine delta. Multiply this by b as well. So we could just actually move some of the terms around. So we will just put ay minus bx cosine delta equaling negative b square root of a squared minus x squared sine delta, like so. And we will just square both sides. So we would get a squared y squared plus b squared x squared cosine squared delta plus, no, sorry, it's a minus. So it's minus a b x y cosine delta, multiply this by 2, equaling b squared a squared minus x squared sine squared delta. And so you could collect the term for the b squared x squared. So it would be b squared x squared plus a squared y squared minus 2ab xy cosine delta equaling a squared b squared sine squared delta. No, yep, sine squared delta. And this is the equation of motion, or basically the trajectory. So it might seem to be something that is very weird, but try to notice this. If you have, let's say, delta to be 0, what you would get instead is b squared x squared plus a squared y squared minus 2abxy equaling 0. This would just become ay minus bx squared equaling 0. Or basically what you know is that it's the same thing as ay minus bx equaling 0, or the negative version. But this works. And so you would notice that this must be y equals to b over a x. Or this is just a trajectory that oscillates, like so, as long as the delta is 0, or basically this is when alpha minus beta is 0. But if you let's say delta to be pi over 2, you would see the following thing instead. A squared, b squared x squared plus a squared y squared, cosine delta would later be 0, and so it would equal to a squared b squared. And technically it's the same for negative pi over 2, so we could denote this to be positive negative. So we would have something like this. And now notice such things. We could divide both sides by a squared b squared, so we would get x over a squared plus y over b squared equaling 1. And and what would you and what you would see here is this would be an ellipse. And so this ellipse here will later depend on literally your a and the b for the length. If I remember correctly, in the x direction, this would be 2a, the major axis, and the minor axis would be 2b. And this is the ellipse. So if you actually later just do the experiment by having the two springs or anything else that has the same type of force, you would be able to see that it is a much more elliptic cycle. And obviously, if you set a and b equal to the same thing, or if we set a equals to b, you could just get yourself that x squared plus y squared is a squared. So this would be a circle with radius a. But maybe later on you might be seeing, if you have the two springs to have different strengths, let's say kx and ky, you instead wouldn't get such curves, but you would get something else which you call as the Lysager's curve. So let me show you one of these Lysager's curve. And so I will show you some of the much more simple ones. So one of the simple ones is something like this. You could have it going like this. I know that my drawing is not really that good, but you could actually just search up the Lysager's curve, or maybe if you want a much more visualized description, you could go ahead and leave it in the comments for me to simulate for you all. And so each of these Lysager's curve has a property that when the kx and the ky is, so if kx over ky is an element of the not the rational, no, it's the rational number, so it's q, it would have a closed path. But if it is not, so this would be closed. But if the ratio between them is irrational, they will never meet. It's something that you have always heard about when you see the visualization of irrational numbers. So irrational numbers will never meet again because it's not repeating instead of a rational number. We can now try to talk about the phase diagram. So the phase diagram is something that is describing the motion of a one-dimensional oscillation. So this is 1D, but instead what you do is that you plot the position and the velocity. It's very similar to the thing that we have already shown on the simulation, in which if you have this damped harmonic oscillation, it would have the spiral going inwards. And so that's the goal of the phase diagram. And so this is what we call as the phase space, and it will result into something which we call as a phase diagram or a phase portrait. So let's recall from the previous derivation that A equals to, no, sorry, x equals to A cosine omega 0 t minus phi, y equals to A omega 0 negative sine omega 0 t minus phi. And so if you notice, you might be able to get that cosine squared plus sine squared must equal to 1, right? And therefore, what you would get is a very elegant conclusion that x squared over a squared plus y squared over a squared omega 0 squared must equal to 1. And this is already straight away concluding that this should be an ellipse. Or this is basically a family of ellipse, because every single a would later correspond to a different ellipse. And you could technically also denote this in terms of, sorry, this should be x dot. And you could technically also denote this in terms of the energy. So it's x squared over 2e over k and x dot squared over 2e over m. So I won't fully derive where this comes from, but you could pretty much see it from the previous equation about the energy. And so therefore, you could get some conclusions as well. Kx squared plus mx dot squared equaling 2e. And so basically each of the curve will later correspond to a certain energy. And because you know for a fact that the energy is conserved, you would also notice that that means that it couldn't change between energies. Therefore, the family of ellipse cannot cross each other. And so if you actually draw it, if this is the x and this is the x dot or the velocity, you would get that this ellipse would go something like this. So the direction is going clockwise instead of counterclockwise. And this will be denoted by a certain energy. So the length in the x direction would correspond to 2e over k. And so you could have something with lower energy, like so, or something with higher energy, like so. But they couldn't cross between each other, otherwise it will be changing energy. So there is another method for you to obtain the phase difference. So you can just try to observe from the following equation here straight away. You could just denote this to be the dx dot over dt is negative omega 0 squared x. And also, you could do that the dx over dt is dx dot. And so you could do a very clever thing in which instead of you thinking about time, you could instead think about the position instead. So it could be dx, multiply this by, obviously, to preserve this should be dx over dt, right? This must equal to negative omega 0 squared x. But notice that this is x dot. So you could get dx dot over, sorry, it's dx dot times x dot would equal to negative omega 0 squared x dx. And so you could do this differential equation. This would be the x dot squared over 2 must to equal to negative omega 0 squared x squared over 2 plus constant. So you would get pretty much omega 0 squared x squared plus x dot squared equaling c, or basically this is just a ellipse. And so it's basically the same idea. We can now talk about the damped harmonic oscillation, or damped oscillation for short. So for a damped oscillation, the f would equal to negative kx minus bx dot, or basically the one that corresponds to the velocity. So therefore, you would get the differential equation to be mx double dot plus kx plus bx dot equaling 0. So let's divide everything by m. So this would be x double dot plus b over m x dot plus kx equal to 0. And now let's actually just transform this into 2 beta as well as the omega 0 squared that we have already defined. And I will tell, and you will later see why we actually denote this to be 2 beta, because it's a very useful way for you to denote the damping. And so if you use the idea from basically from differential equations, you would know that the answer would correspond to two different eigenvalues technically. No, sorry, eigenfunctions. And these eigenfunctions will have the term of the root of the characteristic polynomial. And so in here, the solution of the root would be negative beta plus or minus the square root of beta squared minus omega 0 squared. And this will later correspond to the positive root and the negative root. And so these roots will later correspond to a solution ae to the power of rt. So you could get the final solution to be e to the power negative beta t times a e to the power of squared beta squared minus omega 0 squared t plus b e to the square root of beta squared minus omega 0 squared t negative. And this is basically the general solution. And so what you observe here is there are technically three different cases. So there is going to be when beta squared is smaller than omega 0 squared, which is something that we'll discuss first. And then beta squared to be the same thing as omega 0 squared, and this will result into a much more unique solution. And beta squared to be larger than omega 0 squared, which we call as overdamped. So it's overdamped, underdamped, and this is critically damped. So let's just do the underdamped condition first. So let's just denote the square root of omega 0 squared minus beta squared to be omega 1 squared. And this would mean that the square root of beta squared minus omega 0 squared would be imaginary, right? So we would get something like e to the power negative beta t of a e to the power of I omega 1 t plus b e to the power negative I omega 1 t. And the solution seems to be complex. But actually, if you notice that the complex actually corresponds to a real function of cosine omega 1 t minus phi, if you actually combine these two things together. So more discussions about this within differential equations, but we'll just assume that you know about this. So you would be able to obtain that this would just be a times e to the power negative beta t cosine omega 1 t minus phi. And this is basically a solution in which it is exponentially decaying down and you would have the oscillation dwindling down. It's very similar to the one that I have shown in the simulation shown here, in which the oscillation starts to decay lower and lower. And this is basically what we call as a underdamped oscillation. And so now going back, observing this equation again, this is the amplitude, and there is a oscillation. So instead, let's think about only the amplitude. Let's think about the change of the amplitude over a cycle of this oscillation, in which you have the tau 1 to be 2 pi omega 1. to be the period. And let's try to consider what's the change of this amplitude. So if you take the ratio from the original size, a e to the power negative beta t, and then you divide it by the one after this period, it's a e to the power negative beta t, t plus period, you would get that it decays e to the power beta tau 1. So this is the ratio between the first time and the second time here. And so this is what we call as the decrement, or this is basically what you call as the decaying, basically. Like how fast does it decay? Or you could also denote the beta tau 1 to be the logarithmic decrement. You can also try to figure out what is the energy, and so I won't really discuss it much here, so I won't fully derive it, but you could get that the energy would be actually going something like this. It's like a step going down each time. And if you think about the energy loss, it's it's actually just a function of something like this. So there are some time in which it doesn't lose any energy, but there's some time in which it has this maximum energy loss. And you could actually derive this on your own based on the equation, and you would see the following features straight away. You could also even get the phase diagram as shown here, in which it just goes spiraling down until it reaches the zero, in which it pretty much denotes that the energy is always dwindling down. And that's everything about underdamped. So for critically damped, I won't fully discuss much about the mathematics, but if you take the limit, it will basically correspond to a plus bt of e to the power negative beta t. And this is for omega 0 equals to beta. So this critically damped solution is the best type of damping because it doesn't create this oscillation, but instead it will just go up and then it's stabilized. So it's a much more faster way for you to decay such function. You can technically also try to view the energy as well as the phase diagram, but I won't show it. But I won't show it here because it will later be very similar to the overdamped case. Overdamped, in which omega 0 is the omega 0 is far less than beta. So we will call the quantity squared of beta squared minus omega 0 squared to be omega 2, such that we could actually just denote this to be a e to the power of negative beta minus omega 2t plus beta e to the power negative beta plus omega 2t. And so what you observe is that this is actually a linear combination of two decaying functions. So the first one is guaranteed to be decaying, but the second one could be technically it could be increasing, but because there are limits to this, we know that this value is always less than beta. And so these two are decaying functions, but one of them is decaying much more faster than the other. So there could be three different scenarios the for the trajectory. It could go into a dipping and then trying to go into a stable solution, but it will take much more longer. You could also do it like this. And also, it could actually have the critical velocity such that it doesn't have the overshoot, but it will take a very long time for it to reach the 0 point. And so the trajectory doesn't really give you a very elegant thing for you to see. So maybe you could check for the phase diagram. And it turns out that there is an elegant piece. So let's have these two lines correspond with two different slopes, negative beta, negative omega 1, no, omega 2, and this one is negative beta plus omega 2. So one of the function is decaying much more faster compared to the other. So So most of the paths would be tangential to the negative beta minus omega 2 first, but then it will later correspond to the one that is decaying much more slower. So it will try to go into a tangential component. So it would have like this turning point. So if it goes like this, it's gonna turn and it's gonna result towards zero. So same thing in this direction. And then for the one in between, it would be going like this and then going inside. Same thing here, going in and it will later go much more closer. And this is basically the phase diagram of the overdamped oscillation. So we have seen every single thing in which we didn't apply any force towards the system. So let's start to introduce a sinusoidal force. Sinusoidal driving force. So the force will be F0 cosine omega t. And so this would be added into our entire equation of motion. So it's not that. It's kx minus bx dot equaling mx double dot. So we could write this in general technically. It's x double dot mx double dot plus bx dot plus kx plus the external force. Or you could just divide everything by m to get the following plus omega 0 squared x equaling the outside force divided by m, or basically just the outside acceleration. So to solve such problems, so for this scenario, it would be a cosine omega 0 t, right? So to solve most problems which are linear, you just need to find the homogeneous as well as the complementary functions. The homogeneous one is the one in which the force doesn't exist, which is the damped harmonic oscillation. Depending on if it's overdamped, underdamped, critically damped, whatsoever, it would have this solution with all of the constants. And you would also have the complementary, no, sorry, the particular solution, in which this is one solution that solves this problem. And this could be done literally by trial and error. You could technically also do this by using a much more advanced technique, by using Fourier series and others, but I won't fully discuss that much here, since it is going out of the scope of the physics. So instead, develop that, we'll just guess that the solution would be d cosine omega t minus phi. So we could now expand this solution. So if we try this out, we would get d omega squared of, negative d omega squared cosine omega t minus phi. So we just plug it in, plus, this would be minus 2 beta omega sine omega t minus phi. And another one, plus omega 0 squared cosine omega t minus phi equaling a cosine omega t. So I will skip most of the mathematics, but if you use the property of cosine a minus b as well as sine a minus b, you could just split it into the sine a's and sine a, sine b, cosine a, cosine b. And if you regroup them all together, you can eventually get d omega 0 squared minus omega squared cosine phi plus 2 beta d omega sine phi minus a. This is cosine omega t, which would equal to 2 beta d omega cosine phi minus d omega 0 squared minus omega squared sine phi. This is sine omega t. And now notice something. Left hand side is cosine omega t, right hand side is sine omega t. And these two functions will never meet unless the amplitude is 0. So therefore, you could conclude that this equation must equal to 0 and this equation must equal to 0. Solving it, you could get the d to be a over the square root of omega 0 squared minus omega squared, everything squared, plus 4 omega squared beta squared. And for the phi, it's gonna be 2 beta omega over omega 0 squared minus omega squared. And so the general solution will later be the combination of the homogeneous as well as the particular solution. And this is the general solution for that system. Let's talk about resonance. So resonance is the phenomena in which when the derivative, when the amplitude goes to a maximum at a certain resonance frequency, or basically when the derivative would equal to 0, basically it denotes that there's a local maxima or local minima. So you could just try to solve this just by doing the derivative and figuring out all of the algebra. And so you would be able to obtain that the omega r is actually the square root of omega 0 squared minus 2 beta squared. So this is something that's interesting. Omega 0, the natural frequency for the spring without any damping, would be less than the omega 1. The oscillation of the spring with the damping, and it is much more less than the resonant frequency. And so this is a very useful information for you to know, like approximately how big is the resonance frequency, how big is the natural frequency, and so on. So we can denote how good the damping is using something which we call as a quality factor. So a quality factor is defined to be resonant frequency over 2 beta. So it basically tells you that for a certain frequency, for this resonant frequency, which is where it's maximum. And so this basically tells you about the damping with a certain reference frame. So when the beta goes to 0, the Q would go to infinity, which denotes that it's a very bad damper. But if you increase the beta higher, it would later go to 0, in which its quality is getting much more finer. So you could actually just approximate when beta goes to 0. And so I won't prove it here as well, but you could later prove it by yourself. Is that first of all, is that you could just approximate this to be about omega 0 over the change in omega. And so this change of omega corresponds to the d function. Let's say it's something like this. You take the point in which this is the square root 2 of the height of the total height here. This is the square root 2 and this is the a. Sorry, it's 1 over square root 2 technically. And just measure the distance between these two. And this is the delta omega. So the more sharper it is, the quality factor will like go much more higher. But if it's much more spread out, quality factor goes down. And so depending on the system, it might have a very big value or very small value. And so maybe like you might have heard of something which you call as radiation damping, in which this is type of a, and so this is a type of damped harmonic oscillation, but this is occurring inside of an atom. So if you remember that atoms could like could emit certain energy levels, the energy levels could be damped. And so what this radiation damping is that if you have a charged particle that is oscillating, it is going to lose its energy because of the classical electromagnetism idea of the kink being generated, and thus you need to, and thus it creates a changing electric field. And so this radiation damping could be denoted as a damped harmonic oscillation. And if you plot out And if you try to figure out what's the quality factor is on the order of 10 to the power 7, which is quite high harm compared to a damped harmonic oscillator throughout the world here. So what I haven't mentioned here is that this is actually something which we call as the amplitude resonance, in which the amplitude goes very large. But maybe something else could be resonating. Maybe instead of the amplitude, you might be thinking of the kinetic energy, and that's possible. So the kinetic energy, so basically the average kinetic energy, would just be half times m v squared, right? And the v squared will later correspond to a d and a omega. Divide that by 2 because for cosine squared, the average is going to be around half. And so this value could be easily determined to be m over 4 times, so it's m over 4 a squared, omega squared over omega 0 squared minus omega squared, everything squared, plus 4 omega squared beta squared. So now trying to solve for this maximum condition, omega equals to omega e. So this is what we call the kinetic energy resonance. You would be able to obtain that actually the omega 0 must equal to omega e. No, sorry, omega e must equal to omega 0. So in here we mostly talk about mechanics, in which we talk about F equals to ma. But instead of thinking about F equals to ma, let's think about Kirchhoff's. Why do we think about Kirchhoff's? Is that it is very closely related to oscillation. So we will be talking about circuits. So let's say if you have a voltage generator, a resistor, and then you have a capacitor, and then you have a inductor. The question is, what's the equation of motion of the charge at this particular plate? So this is a very interesting problem. So let's just assume this is a sinusoidal source instead. And we could denote the positive, negative. Well, let's denote it like this. This would be better. So doing Kirchhoff's law straight away, you could get I times R plus the voltage between these two, which is Q over C, plus the voltage between there, it's L di over dt, must equal to the voltage source here. And that's basically Kirchhoff's law straight away. The voltage with respect to time. And so you could just simplify everything straight away. I is dq over dt. So this would be q over c plus q dot r plus l q double dot equaling vt. And so you could divide everything by l. Q double dot plus r over l q dot plus 1 over cl q equaling vt over c. And this is basically a damped harmonic oscillation. You know this is to be the damping, and this would be the angular frequency. And therefore, you could just use the same method to solve the equation of motion of the charge buildup throughout your capacitor. And so there are lots of different physical systems that have this damped harmonic oscillation, even though that they are not really mechanics. But let's now just get away from this segue and jump into the idea of the mathematics behind Fourier series. So the principle of superposition. And this is the idea. If you have, let's say, a linear system, such as the damped harmonic oscillation, it's actually a linear differential equation. So it's L of x equaling ft. Something that I would like to note is that you could actually separate the function to be multiple different functions as well, as long as they result into the ft that you need. And also because this is linear, you could just take the alpha and beta such that the x is alpha x1 plus beta x2 and so on. And then you could build your solution of the operator to be f1t and f2t and so on. So you could build up this final function in terms of multiple different functions as well. So what I showed here is that you could actually just do, so if you have the operator of a collection of equation of motions, x and of t with the a and with the coefficients at the front, this would equal to the sum of the a n, multiply this by the function nt, the in which the operator of this such function would result into the fnt. This is what we call as the principle of superposition in here. So now, if you now think about this, maybe like we could just do the solution that cosine omega nt minus phi would equal to the thing that we have already discovered, right? This is, so it's a times cosine omega nt minus phi is basically the solution of f0 cosine omega nt, right? And so you could do the same thing with the sine. And now based on Fourier's series, Fourier's theorem, all sines and cosines could create any type of functions that you need for the ft. And therefore, you could get the solution of the x based on this only. So, as long as it's periodic, when tau equals to 2 pi over omega, you could just set up the solution for the ft to be just the sum of half of a certain constant, a0, added with the sum from n equals to 1 to infinity of an cosine n omega t plus bn sine n omega t. And you could just denote what an is. An is 2 over tau with the integral from 0 to tau of the initial function that you're interested in, the ft. Multiply this by cosine n omega t dt. And for the bn, it's the same thing, but instead, it's a sine. And so you could just try this on your own to solve certain problems, and it will give you the exact solution after you have already broken down all of the Fourier series and to get all of the constants so that you could just put each of the x's of that solution and just sum them all together. It's basically just the solution of the entire problem. So the final one is we'll be discussing about the response of the oscillator if we introduce a impulsive force. So we'll be denoting two different external forces that will apply to the damped harmonic oscillation. The first is something which we call as a step or a heaviside function. Heaviside function h, which will denote that it will be 0 when time is less than time 0. So we'll denote this to be ht0. And a when time is greater than t0. So it will be a step function like this. It's a at t0. We'll also denote the impulse function to be ht1 minus ht0. No, ht0 minus ht1. We'll denote this to be I t0 t1. So it's basically something like this. So it's t0 and this is t1. height of A. So let's think about the response of the Heaviside function first. So it would be x double dot plus 2 beta x dot plus omega 0 squared x must equal to A when time is greater than time 0. And we'll just assume that the initial case x is 0 and the velocity is also 0. The solution will later introduce first that there exists the homogeneous part, but also there should be A over omega 0 squared, which is one of such particular solutions. And so if you apply the initial conditions, in which I won't fully do it here, it will later simplify into A over omega 0 squared, 1 minus E to the power of negative beta t minus t0 cosine omega 1 t minus t0 minus beta e to the power negative beta t minus t0 divide this by omega 1 sine omega 1 t minus t0. So this is the response of the Heaviside function, as long as the initial condition is 0. Now we could do the same thing for the impulse function, but instead of doing the entire thing literally one by one like before, we can use the principle of superposition. We know that the impulse is just ht1 minus ht0. So we could just use the solutions that we know, which corresponds to initial condition of 0, 0. So we'll also assume that the initial condition is 0. So if we use the previous function and plug it in for our solution, so x would equal to the first solution minus the second solution, this would pretty much already give you the exact solution. It's a very magical trick in mathematics. And so you can just plug it in, and I won't fully open it all up, but we'll just assume when t1 goes to t0, but we will also consider this. When a t minus t0 is still constant, let's call that b. So when we compress everything together for the limit, so this would be the limit, we would be able to get b over omega 1 e to the power negative beta t minus t0 sine omega 1 t minus t0. And now this becomes a much more powerful tool. Let's just state that b equals to 1, or basically this is a unit impulse. And now think about if you try to construct such function. Maybe if you have a random function of force. You could just denote each of these as sort of a impulse, with height equaling to the forces here. Now, because you know each of the solutions of the impulse force when the initial condition is 0, you could just solve for the entire force when the initial forces is 0. And if the initial forces is not 0, you could just add the homogeneous function, tweak it so that you would get the initial position as well as the initial velocity. And that's it. And so this method is something which you call as the Green's theorem or the Green's function or Green's method, in which g, in which you denote the Green's function to be 1 over m omega 1 e to the power negative beta t minus t prime sine omega 1 t minus t prime for time is greater than t prime, and it will be 0 else. And so using this to solve x double dot plus 2 beta x dot plus omega squared x equaling the f over m, you could just get your x to be the integral from negative infinity to time of the force and the green function dt prime. And this is the solution. It's a very fast method for you to solve any type of equation as long as you know what's the Green's function of such differential equation. And that's all for today's video. And so this video is a very dense topic for me to discuss straight away within one video. So if you want much more clarification on each of the topics, you might as well just leave it in the comments for me to discuss later on a future video. And so that's all for today's video. Make sure to like and subscribe, and make sure to share this to your friends who wants to understand physics in a much more deeper understanding. Thank you very much, and I will see you on the next video.